Right, y'all. Let's talk about energy. And so this unit, this what I'm going to talk about right now is kind of an intro to energy, giving you an overview. There are more slides that you're welcome to read through. I'm going to go through this pretty quickly, but please go back and read through stuff. Let me know if you have any questions. Um, so energy, by definition, energy is the ability or capacity to do work. Okay, and work is force over distance, or force through a distance, force times distance. I don't need you to know these definitions. They kind of just set you up for kind of what we're going to talk about. Okay. You have taken physics, you probably are seeing these definitions, have seen them. But yeah, energy is the ability to do work. Okay. Thermochemistry is then the study of the relationship between chemistry and energy. So we're going to talk about calorimetry, we're going to talk about a lot of these other things. And the idea of thermochemistry is what drives these things. Okay. Two types of energy that we've talked about so far broadly: kinetic energy, potential energy. Kinetic energy is the energy due to motion, so how things are moving. It's half mv squared. Again, if you've taken physics, you're probably seeing this. If not, again, don't worry about it. Potential energy is the energy associated with position, so it's where something is, right? So motion, kinetic energy, potential energy, position, how are things staying. Okay. And so if you look at this picture here, right here, potential energy, very high potential energy. So it's stable, it's literally like, hey, what's gonna happen? Am I gonna fall? Am I not gonna fall? Where are we at? Okay. Once you start falling, there's a bunch of kinetic energy. There's a lot of motion going on. And then once you hit the ground, very, very little potential energy because you're essentially stable, like your molecule, like there's heat. In this case, there's heat energy, which is a type of kinetic energy in there as well. Okay, so broadly speaking, two types of energy: potential, kinetic energy. These are kind of the types of energy that we'll talk through in this class. Okay, the SI unit for energy is the joule. The joule is 1 Newton-meter. We talk about joules in chemistry. I think in physics, you guys do Newton meters. The big thing here is be able to convert from one form to the other. I will give you the conversion factors, so I don't expect you to memorize these conversion factors. But if I gave you, hey, stuff in joules, can you convert to calories? If I gave you stuff in calories, can you convert to joules, and so on and so on. Okay. One of the reasons I bring this here, so you guys have probably at one point in time looked at the back of your food and you're like, oh yeah, it's like still a form of energy. Calories, different form of energy. That's probably what you see. Very similar to joules. It's just a different measure. Okay, so like pounds versus grams, kilograms, things like that. All right. When we think energy, there are two broad types of energy: kinetic energy due to motion, potential energy due to the composition, what's in the thing. It's staying energy, if you would. There are different types of energies that fall under, so kinetic, that fall under potential, and we'll talk about those in a little bit. One of the things I'll be testing on you on here is your ability to recognize, hey, which is which? Is this kinetic energy? Is this potential energy? True or false? Those are the kinds of questions that you should expect on this exam. Okay. Again, kinetic energy due to motion. So more movement you have, higher the chemical, the potential, the higher the kinetic energy. Potential energies, chemical energy, we usually store those in bonds. You think about like in place, right? Your bonds are keeping stuff in place. The stronger the bonds, the more the potential energy and things like that. The law that drives thermochemistry, that drives a lot of what we're talking about, is the law of conservation of energy or matter or mass, right? This idea that we don't create or destroy, we just convert from one form to the other. So I can have stuff in that has a bunch of kinetic energy, but then that energy is transferred to potential, or vice versa, again, depending on the kind of reaction that is going on. The relationship between potential energy and stability is inversely related. The more potential energy you have, the less stable you are. Think about it. You have a bunch of stuff. You're like, I'm right here. I have a bunch of energy. What's going to happen? I don't know. And so if you think about this roller coaster, so right here is like, I'm going to like literally just need one tiny push and I tip over, right? And so there's a bunch of potential energy there. And the more stable you are, the less your potential energy, the higher the kinetic energy. So right up here, very, very unstable, but once it goes down and hits like this point, it's like kind of stable, right? It's pretty stable. And so wherever you have more stability, you have more kinetic energy. Okay. Less stable you are, the more capacity to do work, the higher the potential energy. Think about it here. So again, very, very unstable, right? You're like, hey, there's a bunch of energy, I can do stuff with it. But low kinetic energy, very high potential energy. Once you hit here, you're pretty stable. And so you have a bunch of kinetic energy and low potential energy. And then as you go back up, because you're getting back to that kind of unstable spot, your potential energy increases. So again, two types of energy, kinetic energy, potential energy. There are different forms that fall under that. So for kinetic energy, electrical energy due to electricity is one of those. Heat or thermal energy due to molecular motion. So the more motion you have, the more heat or thermal energy. And then light or radiant energy. We'll talk about this in unit 6, maybe 7, later on in the semester, but talk about light and the energy that kind of photons are able to give off. On the flip side, for potential energy, there's nuclear energy and chemical energy. So nuclear energy, nucleus, chemical energy due to the bonds, the positions of the atoms. Okay, all right, so here's a potential question I can ask you. And anytime you're given a true or false question, multiple choice question, kind of think through the things to identify why they are correct or not correct. So correct statement, only kinetic energy can be measured in joules. That's incorrect because energy, period, is measured in joules. Object in motion has a ton of kinetic energy, so that's not a correct statement. Kinetic energy is converted to potential energy as an object falls, also not a true statement because it's potential to kinetic. Kinetic and potential energy are forms of energy, that is correct. Chemical energy is a form of potential energy. Okay, so again, look through these, make sure that you understand the whys between stuff. Okay. So when chemical reactions happen, there's usually some sort of energy change. Usually it's an explosion, there's heat, there are things. But usually matter will possess energy by it's either kinetic or potential, right? It's either due to motion or it's based on the position or composition. And we transfer energy because of the law of conservation of mass. Again, we don't create or destroy, we convert from one form to the other. Okay, so if you think about this picture here, potential energy is being converted to kinetic energy and maybe some thermal energy, maybe some heat is being released there. Okay, and so because of the law of conservation of energy, we can talk about a lot of the things that we're going to talk about the rest of this chapter or unit. So the first law of thermodynamics is the law of conservation of energy, mass. And it essentially says that that total amount of energy in the universe is constant. So you think about a chemical reaction, we're not creating or destroying energy. It's already there. We're just converting from potential to kinetic, from heat to nuclear, or nuclear to heat, and things like that. And so if you think about the system and the surrounding, so we assume that the universe is made up of the system and the surrounding, right? And so if the system is at half tank, the surrounding is at almost empty. When a change in reaction or change in the reaction happens, there's some sort of transfer of energy. In this case, now the system is at almost empty and this is back at kind of middle. Okay, big idea here, the total amount of energy of the universe is constant. There isn't a change in terms of that. So the system we define as what we're looking at. Usually it's our reaction. Okay, so the reaction is happening, that's our system. The surrounding is every single thing else. The glass, the air, the walls, everything else is considered the surrounding. So the system is what we're studying. And again, think back to the law of conservation of mass, of energy. Whatever is gaining, in this case, if the system is gaining energy, has to be gaining it from the surrounding, which means the surrounding is losing energy. If the surrounding is gaining energy, then it has to be gaining it from the system. Okay, and so in order for the total amount of energy in the universe to remain constant, something has to be gaining and something has to be losing. The sum of all the kinetic and potential energies of the things in the system is your internal energy. Okay, so internal to the system. If I'm looking at the system, all the kinetic, all the potential energy is considered my internal energy. And it's a state function that doesn't matter how we get there. It just matters that we start here and we end here. Okay, so there are two types of functions, the state function and the path function. The path function depends on the path that it takes us to get there. The state function does not care. And so if you think about it in this way, for my hikers out there, when I'm hiking, right, this would be a path function, right? I take 12 miles and whatever, this is 5 miles. It depends on the path that I take. That would be a path function. A state function says, I don't care. As long as I get from 0 feet to 10,000 feet, that's all that matters. And so when we think about energy, when we think about these kind of energy of the reaction, it doesn't matter how we get there. It just matters that we start here and we end there. We start here and we end there. Okay. And so that is a state function. And so there are different types of systems, right? We've talked about the system, we've talked about the surrounding, the fact that the system is what we're looking at and the surrounding is everything else. There are 3 types of systems, right? The open system, there's exchange of energy and matter. So like this is an open system, it can go, heat can go in and out, water can, or whatever is inside can go in and out. This is an open system. It's constantly interacting with the surrounding. A closed system only exchanges matter, our energy, right? So heat can come in and out, but nothing else is leaving. And then an isolated system exchanges nothing. Everything is isolated to that system. It's essentially on its own. Okay, so those are the 3 types of systems that we talk about when we do a chemical reaction. Usually we deal with open or closed systems. Okay, again, big thing here. I know it's a lot of talking. Make sure that you're able to kind of recognize what is true, what is not true, and things like that.